Hey, good morning, everyone. Um, it's Monday morning, and this video will be on Chapter 4 um, of Campbell on oxidation. Before getting into it, administratively, so last week I took a midterm exam. We did our first chapter in Campbell, um, and I returned your exam. This video is actually a class behind. On Friday, I sat down to record it, and as I was reviewing the notes, I realized that I never derived the Deal Grove model, and so I started doing that, and it took a little bit longer than I thought. So I didn't get a chance to film the video, so we're a day behind, but I think that'll be all right. We'll catch up. We'll figure out where to get back a day between now and the end of the quarter. I also posted some homework problems. Apologize for the delay on that. That covers the first 4 chapters in Campbell. We'll consider them posted today and do a week from now on the 8th. It's just we'll finish the material for those homework problems by Wednesday of this week. Okay, so without further ado, let's start talking about oxidation. So let me share my screen here. Chapter 4. Doesn't seem right. Let's try that again. Chapter 4. Here we go. Still not convinced. It seems it's acting kind of funny today. Okay, I think that's good. Okay, so in Chapter 2, we talked about silicon substrates, and one of the reasons why silicon has become the dominant semiconductor material is because it's relatively easy to grow very large, very high quality single crystal silicon. But silicon has another advantage, and that is that it is easy to grow an insulating oxide from the silicon substrate. So if you need an insulating layer, right, there's no need to deposit anything additional, different material. You can just oxidize the silicon that's already there, and it forms a good insulating silicon oxide layer. And so today the main topic is just talking about that process, and then we'll spend a little bit of time talking about how you measure, different ways of measuring the oxide layer thickness, and then touch on some other material systems that have been tried but that have some deficiencies relative to silicon oxide as an insulating layer. So the bulk of our time today will be covering the Deal Grove model, which is the model that's used to predict the oxide layer thickness as a function of the growth parameters. And this is important because, right, if you're growing an oxide layer, it's because you need to electrically insulate something in your device. And so you want to make sure that you have a thick enough layer, and not too thick. So having a model to help you predict the time and the temperature and some other conditions required to grow the right layer thickness, and then some measurement techniques to confirm that you have that thickness are useful. So the model that's used is called the Deal-Grove model, and it has two permutations, two main sets of conditions. That would be dry and wet oxidation. And I'm going to derive the model considering dry oxidation just because it's a little bit simpler. So when we're talking about dry oxidation, what we're talking about is the combination of silicon in your single crystal, so in a solid, with oxygen molecule from the surrounding environment to form SiO2. And this model is good for predicting the thickness of thicker oxides, as we'll see a little bit later in these notes. It doesn't do so well for really thin layers. It actually under predicts the thickness, and we'll talk a little bit about why that might be. And so the model basically has it predicts several fluxes at various stages of the oxygen transport. So at the beginning, you have some concentration of oxygen in your in the gas of the oxidation furnace. And so for that oxygen to produce an oxide, it first needs to diffuse across a stagnant gas layer near the silicon wafer. So when you have a flow, right, the flow is moving out here, but as it gets closer to the surface, just as is common in many flow scenarios, right, you're going to have the gas slow down, and so you have this region here where you don't have a flow, and so to get across that stagnant gas region, you need to diffuse through that stagnant layer. Then you need the oxygen needs to adsorb to the surface. Once it's adsorbed to the surface, then it can start to diffuse across the growing oxide layer. And then once it does that, it reaches the interface, and you have a flux of atoms that are reacting with the silicon to form silicon dioxide. And this is a distinguishing factor between silicon and some other oxidation, is that you're growing at the interface, which requires the oxygen to diffuse through the silicon dioxide. If you're growing at the surface, you would require the silicon to diffuse through the silicon dioxide. It goes this way because the oxygen diffuses much faster through the oxide layer than silicon does. Here we can draw on our previous coverage of diffusion. So remember, diffusion has a diffusivity, so there's a constant that is modified exponentially by a term that includes the activation energy and temperature. So this diffusion through the oxide layer is going to increase rapidly with temperature, as we would expect. And also at the interface, as the oxygen is combining with the silicon, right, it is consuming some of that silicon. So you're going to grow an oxide layer, but it's not going to be all growth from the surface, right? I'm going to be consuming some of this silicon. And so the oxide layer grows a little bit into the material and a little bit out from the surface. But growing it at the oxide silicon interface is largely beneficial because you don't have surface contaminants, right? So the surface contaminants are getting kind of bottled up here at the surface of the oxide. The oxygen is diffusing in, and then you have this nice clean interface where there's just not a whole lot there besides the silicon, and so you get an oxide layer interface that has very few impurities. But since this is a diffusion process of the oxygen through the growing oxide layer, as the process continues, right, the oxide layer is getting thicker, which means that the oxygen will need to diffuse further. And so eventually you reach a point where the oxygen no longer diffuses, or the rate slows down rapidly, and at room temperature this produces an oxide layer, right, that's relatively thin, at about 25 angstroms. And so if you want to grow an oxide layer that's thicker than that, right, you need to increase the temperature of the oxidation furnace so that the oxygen can diffuse through a thicker and thicker oxide layer. Generally, the overall reaction here is limited not by the ability of oxygen to get to the surface, but by the reaction rate of oxygen and silicon to grow the oxide, which is good because then we can basically have our reactor shaped any way we want. The geometry is not going to affect it, or the diffusion across the stagnation layer, and it's just going to be driven by that reaction rate. And we'll see this same phenomena where we have transport limited and diffusion limited reactions when we talk about chemical vapor deposition later on. So we'll see this again. I mentioned there's dry and wet oxidation. We're going to use the same model for both. When we have wet oxidation, the difference is that we have water mixed in here as well. And the difference here is that we will have different diffusivities, different reaction rates, and the form for the Diel-Grove model that we look at later will just have a different set of constants for wet and dry oxidation. And wet oxidation is faster, and so you can grow a thicker oxide layer faster, but the trade-off there is that that oxide layer will be less dense. Okay, so the next couple of pages we'll be talking about sort of how we get to our final functional form for the Diel-Grove model. And I've already talked about some of these fluxes in the model. It leaves us with several concentrations that we are interested in solving for. So we have the gas stream concentration, the concentration at the surface after it moves through the stagnation layer, the concentration on the surface as those oxygen molecules adsorb to the surface, and then the concentration at the interface after they diffuse through the growing oxide. And so this gives us several fluxes, right? We've got bulk O2 moving from the stream to the surface, diffusing across the surface, that's J2, and then reacting with silicon would be J3. And so to develop this model, we have to assign functional forms and equations to these various fluxes. So for J1, we have the flux through the stagnation layer. And there are kind of two ways that you can look at this. The first is to look at that layer as a layer that oxygen needs to diffuse through, right? And so you would have some diffusivity of oxygen through that stagnation layer, and then you'd have your gas concentration, your surface concentration, and then the thickness of the stagnation layer, right? So that would be a reasonable way of going about it. However, it is you plug in for this concentration of the gas in the furnace, right? You could use the ideal gas law to give you a partial pressure of oxygen. So you could do that. Typically, what is done instead is to use this convection expression here, where you have this stagnation layer and what they call a mass transfer coefficient across the stagnation layer that's dependent upon the concentration gradient, right? So you still have the concentration gradient, but you're kind of rolling up the thickness of the stagnation layer and the diffusivity into this one constant here. So that gives us a flux for J1. And then J2, remember, is the oxygen diffusing through the growing oxide layer. So this, in this case, we will use the more traditional Fick's first law kind of
expression here where we have a diffusivity through the oxide layer. And this diffusivity, if I go down here and look here, is it takes the form that we saw previously with diffusion, where we have a constant times an exponential with an activation energy and temperature. So like I said above, right, this diffusivity is going to grow with temperature, and that's why you go to higher temperatures if you want to grow a thicker oxide layer. Right, at room temperature, you're only going to grow one that's about 25 angstroms or so. And then we have the two concentrations, so this would be the concentration at the surface and the concentration at the interface and the thickness of the oxide layer, right? So remember, that's going to continue to grow. And then at the interface, we have a flux here where we are consuming the oxygen to form the oxides, right? So we have silicon plus O2 gives us SiO2, and we would have some rate constant here that describes how rapidly that reaction is proceeding in the forward direction, right? That rate constant is K sub S, and so our flux at the surface is K sub S times the concentration at the interface. And so that gives us J1, J2, and J3. At equilibrium, right, we would assume that they are all equal, right? For every, if the concentrations aren't changing, right, for every oxygen that is consumed at the surface, right, one is having to move through the oxide and then also move through the stagnation layer. So we'll assume that, if we have steady state equilibrium conditions for growth, that these fluxes are equal. We don't have oxygen building up at any one point. And so as we'll walk through below, we can use this assumption, right, that J1 is equal to J2 is equal to J3. That gives us two of the equations. We have J1 equal to J2 and J2 equal to J3. That's two equations. We need a third equation, and that equation here is the Henry's law. So Henry's law describes the fraction of oxygen that is adsorbed to the surface, right? That gets us essentially our third equation, and is the tie between C sub S and C sub 0. And here Henry's law, so we have this Henry's gas constant, right, is a proportionality between the concentration on the surface and the partial pressure of the gas. And so using the ideal gas law, we can substitute partial pressure for K, T, and then the concentration. So this will be our third equation for the proportion of the oxygen that is adsorbed to the surface. And so we can combine those three equations and the three unknowns that we have. That would be CS, C0, and CI, as we'll see below, to form an expression for CI, which we can then integrate to give us our growth rate, which gives us this solution to that differential equation here. And a lot of the constants in these laws, right, the D's and the K's and the H's, are in this expression rolled up into these A and B constants. So see here, there's the diffusivity and the K sub S and the H sub G and the Henry's law, gas constant, and the number of oxygen available. And so we'll talk about this a little bit more, but next I want to walk through some of the details of the derivation. This is what I was working on Friday, which kept me from being able to post this in previous classes, previous times that I taught this material. I kind of just said, it's just algebra and a little bit of calculus to get from here to here. And that's what Campbell does, but I thought this time I'd say, well, hey, it can actually work out in math. And I don't consider myself to be overly mathematical, especially for the physicist that started off more as a chemist, and material science kind of leans a bit towards chemistry approach at times. But I had some time, and I figured I was curious if I could get it to work. And so here it is. Again, we have 3 oxygen fluxes, 3 unknown concentrations, and our 3 equations are J2 equals J3, J1 equals J2, and then CO equals HKT CS, right? So here's our 3 equations. We'll start with J2 equals J3. So here we have J2, remember it's the diffusivity across the oxide layer with the concentration at the surface, the concentration at the interface, and the thickness of the oxide layer. And that's equal to J3, which is K sub S times the concentration of oxygen at the interface. Right, so here's our equation 1. Then we take equation 2. We'll solve that for C naught, which we need to plug in here into equation 1. So we have J1, that's the concentration that moves across, that's the flux across the stagnation layer. Remember, so we have H sub G, and then the concentration of the gas and the concentration at the surface equals to J2. That is up here. We already used that, right? That's the constant. That's the flux across the oxide layer. And so we have an expression here that's got CO, CI, and CS. We're looking for to be able to solve for CO so that we can plug it back into our first equation. And so here's where we will add in our third equation, or Henry's law, right? So we solve for C sub S in terms of C sub O, temperature, Henry's law constant, and Boltzmann constant. Plug that in here. Now we need to collect our CO terms, so we'll first distribute this D. Then we will move this CI term to the left side, move this CO term to the right side, factor out our CO, and divide by that polynomial, right? So we have CO as a function of a bunch of constants and CI. So here's where we can take this expression, plug it back into our first equation here, and then start to solve for C sub I. So we take that back into our first equation here. So we have this big monster. So we'll just start to do the algebra that Campbell says, it's just an algebra. But here it is. So first I'm going to move this term over to the right side. Then this says multiply by d sub t. I guess I'm really dividing by d sub t. I'm going to get rid of this term here. So I'm going to divide both sides by d, multiply both sides by t. That actually undoes, right, it leaves c sub I here alone. We will define this h sub g over capital H kt just as little h. That's a simplification that Campbell suggests. So we'll do that, make it a little bit easier. So we'll take this denominator, multiply it by the right side here, and then we're going to multiply these two polynomials. So we do our FOIL multiplication, right? First outside, inside last. That gives us these 4 terms here. So now we're going to collect some of our terms. We'll move this one over because it's got a CI in it. When I subtract this d over t times CI, right, actually I already had that same term, but I was adding it, so those terms cancel. Simplifies things a bit. Now I can factor out the CI, right, so I've got CI times all of this. Actually I didn't cancel it until this step, which leaves us with, we're almost there. We can divide both sides by this polynomial, leaving CI all by itself. I'm going to use this H substitution again to get rid of H sub G over KT, leave it with H, little h times big H here, and we'll multiply by 1 over little h divided by 1 over little h. This is just 1, so that's a fairly common trick. That cancels this little h, puts a little h in the denominator down here, turns this into a 1. Then we can rearrange a bit. just to form the same exact way that it's presented in Campbell. And so we get an expression for the concentration at the interface that's got our gas law, Henry's law, gas constant, partial pressure in the oxygen furnace, our oxidation rate at the interface, the thickness of our oxide, and the diffusivity of oxygen across the oxide layer. Okay, and this matches the equation 4.9 as presented in Campbell, right? He just says, oh, do some algebra. Well, there it is. Okay, so let's see if we can use this expression to confirm some of our intuition about what should affect the rate of oxide growth. So I'm going to take this expression and I'm going to expand it slightly by plugging back in this expression for the mass transfer coefficient and Henry's law constant, right, in K and T, right, because that's buried into this H term. And so now we have this CI concentration. So we'll say, okay, so this CI expression tells us the impact of these different parameters on our concentration at the interface, right? So let's take them one at a time and say, okay, so if we increase the variable, right, what is the impact on the concentration at the interface, and does that make sense with our understanding of the model? So one at a time, let's take anything that's not a constant and say, well, this is something we could adjust. So, so the partial pressure of oxygen in the furnace, right? If we increase that, this would predict that the concentration at the interface goes up, right? Which should make sense. If we had more oxygen in the furnace, we would have more getting across the stagnation layer since it's being driven by concentration gradient. And there's a proportionality constant in Henry's law, so then we would therefore have more adsorbing, which would give us more at the surface and then more diffusing across the oxide layer because of that concentration gradient. So putting more on one end will eventually lead to more at the other end, more at the interface. That makes sense. What happens if we could increase the rate of oxidation at the interface? Well, here we have it in the denominator. So if we increase the rate of a reaction at the interface, the concentration should go down at the interface. So that makes sense, right? We are reacting it more quickly. There should be less there. H sub g, this is the mass transfer coefficient. If we could increase that, right, that would get more across the stagnation layer, which would drive our concentration gradients and produce more at the interface, similar to increasing the partial pressure. If we can increase the temperature, right, which we need to do to grow thicker oxide layers, the concentration at the interface should go up, right? So we have the temperatures in the denominator of the denominator, right? And so that actually leads to an increase in the concentration. So increasing the temperature of the furnace increases the oxygen pressure in the furnace just due to the ideal gas law. It would also increase D, right? So we jump ahead and talk about D, right? D is also in the denominator of the denominator, meaning that if you increase T or D, you increase the concentration at the interface. Remember, this D is temperature dependent, right? This is equal to D naught diffusivity times E to the minus Q over RT. And so we have a T down here. We also have a T here that drives this to be larger. So T and D actually move together, but both of them increase the oxygen concentration at the interface, which makes sense. Where if we have a higher temperature, we can diffuse more of that oxygen through the growing oxide layer, which is why to grow an oxide layer thicker than about 25 angstroms, you have to go above room temperature. And as the oxide layer grows, right, it's a further distance that the oxygen needs to diffuse, And so that's predicted here that the oxide layer grows, that concentration should decrease, right? So a lot of this makes sense with our intuition about what's happening with the model, which is good. Okay, so we have an expression for the concentration at the interface, but we don't yet have a growth rate, which is what we need to predict the thickness as a function of time. So to get a growth rate, we're going to combine the flux, right? So we have the flux at the surface. This would be in atoms per area per time. And then we have an oxygen concentration per volume of SiO2, right? So the growth rate, we're growing SiO2. So as we are moving oxygen atoms to that interface, they are becoming SiO2. So the growth rate that we get is a combination of how many of them are arriving at the surface and how many are being incorporated into the volume, right? So we have a flux divided by a volume. This volume would be atoms per volume, or I guess a concentration, a density. Sorry, this is more of a density, atoms per volume. So if we just look at the dimensional analysis, right, we have atoms per square meter per second divided by atoms per cubic meter gives us meters per second. So we have a thickness, a growth rate of thickness in distance per time, which makes sense. All right. So we have this growth rate, we need a flux. Which flux do we pick, right? Well, we want the one at the end where we have the flux at the interface. We have the number of atoms actually reaching the interface where the reaction is occurring and the oxide is growing. If you recall, one of our assumptions in deriving the model was that J1 equals J2 equals J3 at equilibrium. So we have this flux. This is K sub S, our reaction rate, times our concentration at the interface. This is what we derived above. So we'll plug that in here for our J, and then we're going to divide it by N sub 1. This would be the density of oxygen in our oxide, right, to give us our growth rate. Now our growth rate, right, if we're talking about a rate, we're talking about a change in oxide thickness per time, right? So we'll look at this equation here. And this is the one that we need to integrate in order to get an expression of oxide thickness as a function of time. One of the boundary condition here is that we have some initial oxide layer just due to the environmental conditions before we start our oxidation. Remember, we're going to get a surface oxide even at room temperature. So that's kind of what we're thinking about as in terms of T naught. So before we even start, we're starting with some oxide. We're not starting with a pure, clean silicon surface. And so we'll apply this boundary condition, and then we'll solve this differential equation. It's not overly difficult, but Campbell doesn't do it at all. He just says, solve it, here's what you get. So to solve it, right, you've got this rate here. So I'm going to move over the denominator. It has my T ox in it. So I'll move this up here, move the dt over to this side, and then integrate. This is just a simple polynomial, right? So we pick up a T ox on these terms here, and then a T ox squared over 2 on the last term. Here we're just going to pick up a T, and then we'll add our constant of integration. After we integrate the differential equation, we're left with this line here. Then we'll apply our boundary condition, right? That we're at t equals 0, we have T ox equals some T naught, some initial thickness. So we'll plug in T naught for T ox, we'll plug in 0 for T, that knocks out this term, which leaves us our constant equal to this collection of environmental constants and our initial oxide thickness, right? So we'll take that C that we found by applying our boundary condition, we'll plug it back in for the C that we had above, which okay, rewrite it down here, make sure I didn't make a mistake, KS, yes, right? So I'm just basically rewrote that twice. So we'll plug in for C here, which gives us this expression, right? And now it's just an exercise of solving for T ox. sorry, let me refresh my memory. Yeah, we want an expression for Tox that's as simple as we can make it to make it easier to use. So these next couple lines are just simplification exercise, right? So here we'll take this big long expression. I want to isolate this Tox and Tox squared. So since this is divided by 2d, I'm going to multiply every term by 2d. That knocks out the denominator here and here. Next, I'll multiply all terms by 1 over k sub s to further isolate the Tox squared, so that's going to knock out the k sub s here, here, and add it to the other terms. Then I'm going to collect all of the, so Tox squared is by itself. Tox here, I'm going to collect all these Tox terms and factor out the Tox. So then I'm just left with a collection of constants, right? Here I'm going to make one assumption, and actually I'll jump down where I cover it. So before we added Henry's law, that was our third equation. And actually, to derive the finished form for the Deal-Grove model, the assumption is made actually that Henry's law constant times kt is equal to 1. Right? So basically what we're saying is that h is equal to h sub g. Because if you look at that, that's how we're defining this h is h sub g over hkt. So if hkt is equal to 1 in Henry's law, basically what we're saying is that the concentration at the surface is the same as the concentration sort of near the surface is the same as the concentration of oxygen adsorbed to the surface, right? So that's what we mean by Henry's law. This hkt equal to 1 is just that the concentration there is the same. So that simplifies this expression a little bit. So everywhere there's an hkt, it can just go to 1, which means that the constants times Tox is just 2d times 1 over k sub s plus 1 over h sub g, right? So we're going to collect these constants together and just call it a. So now on the left-hand side we have a times Tox plus Tox squared. So we'll start to work on the right-hand side. I have some things I can cancel from before. I can substitute this hkt here as well. And then I have some T naught, that's my initial oxide concentration, and T, here's my thickness. This is my x variable for this model expression. So I have a collection of constants times that T variable. I'm going to just collect those together and call it B. And then all of the constants here, right, this initial oxide layer thickness is also a constant. So I have this huge collection of constants here. I'm just going to collect those together and call it tau. Right, so now I have Tox squared plus A times Tox. That should be an equal, sorry, not a plus, equals B times T, which is time, plus tau. Right, there's a lot of constants buried in there, and these constants come from our expressions that we used to build this model. But we can simplify tau a little bit. So I'll do that here. Right, we'll factor out this n sub 1. This is the concentration of oxygen in the silicon dioxide, H and P. And I'll factor out 2D also. Right, this conveniently is the same form for B that we had defined above. So we can define tau in terms of A's and B's also, which is nice. This is actually the inverse of B, so it's 1 over B. So that puts a B in the denominator over all of this stuff. Then I will do a similar trick. We'll factor out T sub D here. And once we do that, we get A, right? A times T naught. So our tau looked kind of nasty, but if we put it in terms of A's and B's, it gets simpler just like we saw above. So we have tau is A times T naught plus T naught squared over B, right? So this matches Campbell's expression 412 in the text. And also here we have a match to equation 411. So that was nice after spending most of the afternoon Friday getting to that result. Okay, so that's how you get here. This is the final form for the Deal-Grove model. We have this Tox squared plus A Tox equals B times T plus tau. And there are two limiting cases of this model, right? So if we have a really thin layer, right, we have Tox is little, and so if we square it, it gets even littler, which means that we can neglect it. So we'll throw that part away, and for thin layers, we can simplify this model to Tox equals to B over A, right? Those are our constants. And these are all constants, so this is itself a constant. So we have a constant times T plus tau, which is more constants. And so we have this linear rate coefficient, right? So that tells us that the thin, at the beginning, we're going to have a linear growth for the oxide. But as it gets thicker, we have the other limiting case, right? So if Tox is big, then we have a big number squared, which gets bigger, which means we can throw away the A times Tox term. And we have this approximation, right, where we have Tox squared equal to B times T plus tau. And so here, it's squared, so we have this parabolic rate coefficient. So what we're seeing here is that for thick layers, the Tox is slowing down, right? Which makes sense because as we're getting thicker, it becomes harder to diffuse that oxygen across the layer, the growing layer. Okay, so we have oxygen and silicon reacting together. In some cases, a little bit of chlorine is also used. This is mostly to provide a sink for metal contaminants, so they will react with the chlorine and result in fewer impurities or a better interface for the oxide. It also catalyzes the reaction to a certain degree and gives you a faster reaction rate. And like we saw here, right, the oxidation slows as the layer thickens. And so to get thick oxide layers, we need high temperatures or long times. You can increase the oxidation rate by increasing the partial pressure of oxygen, right, and have a high pressure furnace, which we saw above when we looked at the concentration at the interface, right, increased with the partial pressure of oxygen. And also, so when we derived the model, right, we had a lot of, we had the diffusivities, we had mass transfer coefficients, and you say, okay, so that's nice, you can define that as a variable, but like when you're going to go to calculate this, like what do you use for that number? And the answer is that you don't use a number for those. They lump all those constants together in A's and B's, and then they just determine the number for the A's and B's, and they do that experimentally, right? So you're gonna do a bunch of experiments. You're gonna run silicon through your furnace at different times and temperatures, or different times for whatever temperature you're running at, and then you can fit the data to this linear or parabolic expression and extract what the A's and B's should be under certain conditions, right? So they're determined experimentally. And so here's a table 4.1 from Campbell, which gives you the A's and B's and the taus for wet and dry conditions as a function of temperature, right? So these are what you need to do the homework problem and to calculate oxide layer thicknesses in practical applications. So, and the Deal-Grove model fits the data pretty well, especially for thicker oxides. I think I mentioned earlier, it does break down when the layer is very thin, right? Because you have a different mechanism that's going on that's not included in the model. And Campbell goes through a bunch of different explanations for why this might be. A lot of people have studied this and tried to and put forth hypotheses for why you see an increase in the growth rate at low oxide layer thicknesses, and the model's not capturing this.
reading those explanations, it seems that the best one that's cited is that when the oxide layer is very thin, right, you're not having growth just at the interface, right? Because the layer is so thin, you'd have a certain amount of intermixing of silicon and oxygen throughout the whole thickness of the layer. So you've got growth throughout the whole thickness, not just at the interface, which means that the rate is much higher in those initial stages. As the oxide layer gets thicker, you only have growth at the interface. Okay, so I'm running up on time, so I'm going to try to finish this a little more quickly. And so what result do you get? You get silica. You get SiO2. It's grown relatively quickly, and so you don't get crystalline silica. You don't get quartz on the surface, right? You get fused silica, which is amorphous, which means that you don't have long-range order, but you do have short-range tetrahedra, right? You've got these silicon is bonded to 4 oxygen, right? And then those oxygen are bonded each to silica, so you have these kind of loose network of these SiO4 tetrahedra. And then you can also, within that network, have network modifiers. These are other atoms that change, that impact the formation of that network. And in some cases can improve the properties of the oxide. I mentioned at the beginning that we'll cover the Dilgrove model and then talk about some ways that the oxide layer is measured, the thickness is measured. The simplest way would just be to mask off a part of the surface. So I'm going to cover the surface with something that is non-reactive, and then I'm going to apply an etchant. We haven't talked about etching yet, but that would be like an acid or plasma or something that will remove the oxide. And in general, the oxide is going to etch much easier than the silicon, and so when it gets to the silicon, it's going to slow down very significantly. And so then you can remove the etchant and then image the surface either with an SEM, scanning electron microscope, or a TM, transmission electron microscope, or a surface profilometer, which is essentially just like a little needle that goes across the surface and measures the profile. And you basically measure the thickness of the oxide by looking at the depth of the step. This is destructive, and it assumes that the oxide etch is much faster than the silicon etch. Oh, excuse me. I forgot I didn't plug in my computer and it's going to die soon. Okay. And so that mask and etch and image is destructive, but it's fairly straightforward. There's also light-based and electrical techniques to measure the oxide layer thickness. For the light-based techniques, you can use ellipsometry, which is a little more difficult to understand, but you look at the ratio of reflected polarized light from the surface at different angles, and you can extract the layer thickness from that. This is non-destructive, but you need to have a relatively large area. You can also look at the interference as a function of wavelength, and in this case, what you have is light shined onto the surface normally, and you're going to get a reflection at the top of the oxide layer and at the bottom of the oxide layer. And what you see is interference of those two beams, and where you see interference maximum and minimum, right, the distance and wavelength between those tells you what the distance is between that top and the bottom interface. And so if you were in material 680, right, we saw these interference fringes when we did the FTIR experiment, where we were looking at the different thicknesses of the polyethylene film. And we saw these oscillations in the baseline, and you can use that information to figure out what the thickness of the layers are, right? So this is the same sort of idea, only you are looking at the thickness of an oxide layer on the surface of silicon, not of a polymer film. There's also several different electrical techniques, and in these cases, generally, you're turning the oxide layer into some sort of an electrical device.
You can turn it into a capacitor where you would have a potential difference across it, and then you just increase the potential until you have breakdown. And the voltage at breakdown tells you the thickness. It also gives you a measure of quality. You can run this in different ways. You can increase the voltage until you get breakdown, or you can go to a set voltage and just hold it there and measure the time until breakdown. You can also measure the capacitance of the layer. This also differs with interface quality. It can give you some information about which ions are mobile and traps within the band gap. So you have a set of electrical, light-based, or kind of direct measurement techniques for assessing the oxide layer thickness. Okay, gotta finish up here. Okay, so what happens if you have doped silicon? Right, we talked about growing on crystals and adding in impurities. How does that affect the growing oxide? Well, if you recall our discussion in the last lecture about growing silicon crystals and the segregation coefficient between the liquid and the melt, right? There's also a segregation coefficient between the oxide and the silicon, right? And so those impurities will have a tendency to collect in either the oxide or the bulk silicon, and so you have a segregation coefficient here as well, and that depends on the speed of the growth, right? Because those impurity atoms have to diffuse, right? So there's a dependence there on the temperature at which the oxidation is occurring, and also on the time that it takes to grow that oxide layer, and in addition to the segregation coefficient. And you're going to have a different segregation coefficient for each impurity, right? So some of them tend to remain in the silicon, others tend to segregate into the growing oxide, and so it depends upon the conditions that you grow your oxide layer on, and also what dopant you're talking about. But this is important because, right, if you get this wrong, then you're gonna you could potentially leach out impurities from the silicon, or change the properties of the oxide layer. Right? If you're going to leach these impurities in there, you might be making it less insulative than you had planned. Okay. And the first thing I said in this lecture was that silicon, one of the reasons why it's great is because you can grow a nice oxide layer from the bulk material. But then you're stuck with the properties of silicon, and for certain applications you might want to have a higher dielectric constant, or reduced impurity diffusivity, so that the impurities don't get to your active region, and so forth. So you might want to switch to a different material, say silicon nitride. Silicon nitrides do give you these better properties. However, they don't have as nice of a interface as silicon dioxide and silicon does, because nitride actually grows from the top, right? So you don't have growth at the interface where everything is clean. You grow it from the top where you have your impurities, and also you have a bigger difference here, an expansion coefficient between the silicon and silicon nitride. And to get high permittivities, they've done things like deposited other films on top of silicon. It's tough to get silicon directly to these other films without a layer of SiO2 in between, because SiO2 forms rapidly. When exposed to any oxygen environment, you get a very thin layer, and it's tough to deposit that without that thin layer forming. Let's see here. Oh, one thing, I know I'm out of time, but one thing I want to say here at the end is with this tau, right? So why do we have this tau here? How should we think about this in terms of the deal growth model? So going back to this model, right, you can think about tau as essentially right? It's compensating for the initial oxide layer thickness that you had when you started. And you add it to your time, right? What you're basically saying is that at time t equals to 0, it's not actually 0 because I had this initial thickness, right? So if I want to go back to actually 0, right, I would need to subtract tau, right? And it's essentially kind of going back in time to get back to this, 0 oxide state. So I can think of it in terms of, a head start, so to speak. Okay, so I'm over on time. We talked about the Diel-Grove model. We developed it, and then talked mostly about measuring the oxide layer thickness, right? And this is done to give an insulating layer to isolate different parts of your electrical device.